Once upon a time, there was a little boy named Michel. Oh, okay. So 3.2 is all about Rolle's theorem and the mean value theorem. We're just going to do this in two parts. So today we'll talk about Rolle's theorem. Michel Rolle was a French mathematician. He decided to write a theorem saying, let f be continuous on the closed interval from a to b. So stop there. Think about what continuous means. No jumps, no holes, no vertical asymptotes, no oscillations. And then differentiable on the open interval. So that means all those same things, but also no sharp turns and no vertical tangents. The continuous part has to be continuous at the endpoints, so A and B are included, so no holes at the endpoints. Nothing weird going on at the endpoints, like vertical asymptotes or anything. But differentiable just between A and B, so there can be like a sharp turn right at the endpoint, which would be weird. But there could be a vertical tangent right at the endpoint, which would be weird. But anyway, that's the conditions of Rolle's theorem. And if f of a equals f of b. So what does f of a mean? It means if you plug a into the function, that y value equals the same y value that you would get if you plug b into the function. So think about what that means. The two y values at the endpoints are equal, but in between, there's nothing weird going on. Okay? Then there's at least one number, c, in AB. So in between A and B, there's another number, we'll call it C. There's at least one number, so that the derivative at that point equals C. So what that means is between two values, x values A and B, there's at least one place where if we take the derivative of the function and plug C into it, we get a value of 0. What does that mean if the derivative equals 0? Horizontal tangent line. So what's going on at a horizontal tangent line? We have either a maximum or a minimum, or a possible just flat spot where it might increase and then flatten out and then increase again. So there's at least one place in between A and B. Could be everywhere between A and B, because if f of A is here and f of B is here and it's a straight line in between, then they're all equal. All the derivatives there would be equal to 0. Or it could go up and come back down as long as f of A equals f of B. So these two y values would be the same. Here's A, here's B. It could go down like this. So here's a place right here, we'll call that C, where there's a horizontal tangent. Or it could be like three places. F of A, f of B are equal, horizontal tangent here, horizontal tangent here, horizontal tangent here. So here's one of them, here's another one, and here's a third place. Third value of C in between A and B that has a derivative that equals 0 at that point. Alright, so yeah, he's pretty amazing to figure that out, right? So what are the three conditions of Rolle's theorem? Because on the AP test, they will ask you if Rolle's theorem applies, or they'll ask you something about a function and you have to think about if the three conditions fit. So what are those three conditions? The first condition is that the function has to be continuous on the closed interval. The second condition is that the function has to be differentiable on the open interval. And the third condition is that the derivative at C, and no, I'm sorry, that's the conclusion. Thinking ahead. That f of A has to equal f of B. And then what's the conclusion? The conclusion is then that there's some place in between, we'll call it C, where if you plug C into the derivative, you get a 0. So this is going to be an interactive video. Tomorrow I'm going to check a couple things on your notes. So even if you don't need to take notes, which you should write down at least these three things in this conclusion. I'm also going to check this picture, draw a picture or graph that demonstrates what Rolle's theorem says. I'll show you this one. Just an example, you can have your own picture. Here's f of a, here's f of b. Somewhere in between here we're going to have at least one horizontal tangent, one place where the graph has a horizontal tangent. So in this case it's here, here, and here. So here's the one value, here's the other value, here's the other c value. So you have to draw some picture that demonstrates Rolle's theorem, making sure that your f of a equals f of b. Alright, that's one thing I'm going to check tomorrow. And then here, I'm going to check these three things. Draw an example of three graphs where each one fails one of the three conditions of Rolle's theorem. Discuss how Rolle's theorem does not necessarily apply. So draw me a graph that's not continuous between A and B, and show me that there isn't a place in between A and B that there's a horizontal tangent. So you have to draw a graph so that the derivative at some place in between A and B does not equal 0, that there's no place in between A and B where the derivative equals 0 because it's not continuous. Here, draw me a graph that there's no place where the derivative equals 0 in between A and B because it's not differentiable. And here, draw me a graph where the y values are not equal, so then you can't find a place in between where the derivative equals 0. All right? So we're looking for examples of why Rolle's theorem does not work because one of the three conditions was not met. All right, in this example, find the x-intercepts for f of x and show that the derivative equals 0 somewhere between those two x-intercepts. So what does this have to do with Rolle's theorem? Well, if you think about any kind of graph, the x-intercepts are two places where the y value equals this y value, where these two y values are equal to each other. And we know this is a continuous function. So first of all, condition number 1, f is continuous because all quadratic functions are continuous, all polynomial functions are continuous, and differentiable. We know it's differentiable because there's no denominator that would make it equal 0. It's not a piecewise function. There's no absolute value, which would have a sharp turn. There's no oscillations. It's just a plain old polynomial, so everything's good. And the third condition, f of a equals f of b, because they're x-intercepts, right? So where are those x-intercepts? Let's find a and b. That's what we have to do. So where does this equal 0? Notice this is not the derivative equal to 0. We're just finding x-intercepts right now. So we would factor it to x, x and x. Unless you'd prefer to use the quadratic formula or graph it. You could graph it on your graphing calculator. Or we could just do old school factor. Set each factor equal to 0, add 1 to both sides, add 2 to both sides. So we get x equals 1 and x equals 2. So obviously that's a very bad picture. It's more like, okay, and I know this is a parabola, right? And because the coefficient of x squared is 1, positive 1, we know it opens up. So it's going to be like this. So this is 1 and this is 2. All right. So our x-intercepts are here. So we found the x-intercepts for f of x. And it says show that the derivative equals 0 somewhere between them. So the show that part means that we're going to use Rolle's theorem. Condition number 1, 2, and 3 are met. So Rolle's theorem applies. So like back in geometry, we can say by Rolle's theorem, because Rolle's theorem applies, there exists at least one c in the interval from a to b such that the derivative equals 0. So because we've shown that the three conditions for Rolle's theorem the three conditions for Rolle's theorem can be are true, then we know by Rolle's theorem that there's a derivative somewhere in there that equals 0. It didn't ask us to find it, it just said show that somewhere between them there is one. But if it said to find it, or find them, what would we do? we would take the derivative, so the derivative of f of x, 2x minus 3, and we'd set that equal to 0, and then we solve it. So add 3, divide by 2, x equals 3 halves is the value of c that makes this derivative equal 0. So that's where a horizontal tangent is, at x equals 3 halves. Right in between, which we knew, that's pretty logical for that one. All right, next example. Determine whether Rolle's theorem can be applied, and if so, find all values of c in -2 to 2, such that the derivative equals 0. I didn't write down the function. That's weird. All right, I don't have it. Hang on a second. Oh, it miraculously appeared. All right, there it is. Sorry about that. And these are supposed to be open interval values. So this is the correct example. Determine whether Rolle's theorem can be applied, and if so, find all the values of c in the interval from -2 to 2, such that the derivative equals 0. So first we have to see if all the conditions of Rolle's theorem are satisfied. So is the function continuous? Yep. Everything's good. Now, if there was a denominator here, like if it was something like x plus 4, where would this not be continuous? It would not be continuous at -4. Well, that's not in our interval, so that would still be okay, because it just has to be continuous from -2 to 2. All right? So check those things out. This one's continuous everywhere. And secondly, it's differentiable everywhere also. Polynomial functions are continuous and differentiable everywhere. Third condition, does f of a equal f of b? We better find out. So what's f of -2? So we need -2 to the 4th minus 2 times -2 squared. 16 minus 2 times 4 is 8. All right, let's put in a positive 2. 2 to the 4th minus 2 times 2 squared. 16 minus 8. Still 8. So yes, f of b equals f of a. So then we know that Rolle's theorem applies. So we know there's somewhere in between -2 and 2 that the derivative equals 0. So let's take the derivative. 4x to the 3rd minus 4x, set it equal to 0. We can factor out 4x, so we get x squared minus 1. And we can set each factor equal to 0 right here. Or if you wanted to, you could factor this again, but it'll work out the same if you remember that when you take the square root of both sides, there are 2 possible answers. If you had decided to factor it, you'd have x plus 1 times x minus 1, and if you set both of those equal to 0, then you for sure get your 2 answers. So just make sure when you take the square root, you get 2 answers. And here, if you divide by 4, you get 0. So we've got 3 answers. 1, -1, and 0. Are they all in this interval? Yep, they are. So those are our 3 values. All right, there's your homework, page 176, 1 through 29 odd, and that's part 1 of 3.2.